Hello, we're back. Bob and Annie here, and we've got another video cast for you. The purpose of today's video cast is to fill you in on some of the topics from Chapter 5 relating to gas laws that we did not cover in the introductory chemistry course. So today we're going to talk about Dalton's law of partial pressures, calculating the average kinetic energy of a gas particle, and calculating the root mean square velocity of a particle as well. So let's begin with Dalton's law of partial pressures. You saw this briefly when we talked about how when you collect hydrogen gas by bubbling it through water, there's actually a mixture of hydrogen and water vapor. Let's expand on that a little bit. Dalton's law of partial pressures says that the total pressure that a mixture of gas exerts is simply equal to the sum of the partial pressures of the two gases, or however many gases there are that make it up. Okay? Well, what is the partial pressure? The definition of partial pressure is the pressure that one of the gases in the mixture would exert if it were by itself in the container. So for example, let's say that I've got a gas here, as indicated by the red dots, and I combine it with another gas, as indicated by the green dots. The pressure that each one would exert if it were all alone in the container is called the partial pressure. However, if I were to combine those gases in the same container, same volume and same temperature, the total pressure that they would exert is equal to the sum of the pressures they would exert if they were separate. So we simply add them together. Okay? Now, let's look into this in a little bit more detail. So there's our definition of Dalton's law of partial pressures. The total pressure is equal to the sum of the partial pressures. Okay? Well, what I can do is use the ideal gas law, of course, which says PV equals nRT, to write an expression that shows how each individual partial pressure depends upon the number of moles of gas. So I can say, for example, P1 is equal to N1 RT over V, where N1 refers to the moles of gas number 1. Well, I can simply now write out Dalton's law of partial pressures as follows. The total pressure is the moles of gas number 1 times RT over V plus the moles of gas number 2 times RT over V plus dot 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 plus the moles of the nth component, however many components there are, times RT over V. Can we do anything to simplify that, Annie?
Yeah, you can factor out the RT over V to get the...
Want to show us?
Sure, to get equal, so it'd be N1 plus N2 plus dot 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 N. All of that times RT over V.
Excellent, excellent. Because the gases are all in the same container, the temperature is the same, the volume is the same, and of course R is always a constant, so we just factor that out. Well, that makes our life easier now, because what is N1 plus N2 plus dot 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 plus NN?
That's just the total number of moles.
Very good. Show us what that simplifies to then. Just replace that with N total.
Equals N total RT over V.
Fantastic. We'll set that equal to P total, and we'll draw a big box around it, because this leads to a pretty important concept, and that is, when you've got a mixture of gases in a container, the total pressure that that mixture exerts does not depend upon the identities of the individual particles, it only depends upon the total number. Okay? So that lets us solve some moderately interesting problems. So let's consider this. A mixture of gases contains 5 grams each of nitrogen and fluorine. They're in a 2-liter container at 25 degrees Celsius. So your problem is to calculate the partial pressure of each gas, that is the pressure that the nitrogen and the fluorine would exert if they were by themselves, and then the total pressure. Take it away, Annie.
So first, let's solve for the partial. Okay, the partial pressure of N2 gas. So that would be, you would take 5 grams of N2, because nitrogen is diatomic in
Correct.
gas form.
Correct.
And then you want to find the number of moles, so you would divide that by its molar mass, which is 2 times 14.01 grams per mole to give, what is it?
0.13.
0.13.
Oh, I'm sorry, take that back. 0.178 moles.
0.17
8 moles. We can
7, 8 moles of N2. So then P is equal to N RT over V. So the P N2 is equal to 0.178 moles over 1 times 0.08206 liters atmospheres over mole K times 273 plus 25K over 1. Because you're going from, you have the Celsius, but you want to get the Kelvin, and then you divide that all by 2.00 liters, and you can and then when you cross out the units, you get atmospheres,
Very good.
which is equal to
2.18 atmospheres.
2.18 atmospheres for
Great.
PN2.
Great. Okay. So using the moles of nitrogen, Annie calculated the partial pressure of nitrogen, that is the pressure the nitrogen would exert if it were by itself.
Yeah.
So now let's do the same thing for fluorine.
So should I extend the
Yeah.
page?
Yeah, go ahead. That's fine.
Okay. So the PF2 would be 5.00 grams of F2 divided by 2 times 19.00 grams per mole to give
0.132.
0.132 moles of F2, and PF2 would be equal to 0.132 moles times 0.08206 liters atmospheres per moles Kelvin times 273 plus 25K over 1, all divided by 2.00 liters. So PF2 would equal
1.61 atmospheres.
1.61
Great. So now that we've calculated the partial pressures of the two components of the mixture, that is the pressures they would exert if they were by themselves in the container, what do we do to calculate the total pressure?
You could just add them together.
There you go.
So P2 is equal to PN2 plus PF2, which is equal to 2.18 plus 1.61 atm, which is equal to
3.79.
3.79 atm. And you can run a nice box around that.
Awesome. Excellent. That is a good example of the application of Dalton's law of partial pressures to calculating the total pressure. Now, let's go back a bit, and we saw before that the total pressure depends only on the total number of moles of particles, not on their identities. So that tells us that we should actually be able to solve this problem in a different way. That is, rather than calculating the partial pressure of nitrogen and fluorine separately and adding them together, could we not simply add together the moles of nitrogen and fluorine to get the total number of moles of particles and then plug that into PV equals nRT? Let's try that.
So the moles of N2 equal to something, and the moles of F2 is equal to
What, 178 moles of N2?
0.178 and 0.131, right?
132.
Of 2
Okay.
moles. So P2 is equal to N2
RT.
RT over V, so that would be equal to 0.178 moles plus 1.132 moles times 0.08206 liters atmospheres per mole
There you go.
I'll be it on.
Hey, by the way, Annie, do you know what 25 degrees Celsius is in Kelvin?
It is 298 Kelvin.
Very good. Good thing to memorize.
298 Kelvin over 1, all divided by 2 liters. And when you plug that in, P2 is equal to
3.79 atmospheres,
3.79
which is the same value you got when you calculated the partial pressures separately and simply add them together. So you can use either method, whichever one appeals to you. Okay?